All right, so hopefully you've gone ahead and tried this on your own. We're just going to go through the same process and derive the coefficients for a third order Taylor polynomial. So we have a polynomial of degree 3, and we're modeling the function e to the x near 0. All right. Now, you may have noticed a pattern in the derivatives of e to the x, right? So it's pretty easy to come up with the derivatives, right? The the first derivative is e to the x. The second derivative is e to the x, and so on, right? So you can see that f prime, all the derivatives at 0 are going to be 1. Okay, so we'll just kind of hold that thought. So let's just take a look now at all the derivatives of this p3. All right, so the derivative of what we're calling p3 of x is equal to, again, the constant term goes away. We get c1, c1 plus 2c2 times x plus 3c3 times x squared, right? And if we look at the first derivative at 0 of that function, put in 0, everything goes away except for c1, right? And I know that f prime at 0 is 1, right? So that tells me that c1 is equal to 1. All right, just like we had before. Let's look at the second derivative of this polynomial. The derivative of the derivative, we're going to end up with 2c2, right? The c1 goes away. We take the derivative of 2c2 times x. We get 2c2. And then we're going to have plus, I'm going to write this as 2 times 3, right? It's 6, but times c3. All right. Oh, and x, right? Okay. So let's look at p3, the second derivative at 0, and we just end up with 2c2, and that we want to match the derivative of the e to the x function at 0, which is 1. So we get c2 is equal to 1/2, just like we got in the previous example. So let's go on and look at the third derivative. Okay, so we want the third derivatives to match as well. So take the derivative of the second derivative. We get the third derivative. So this is a constant. 2c2 is a constant, so that goes away. And so we have 2 times 3c3, right? And now we want that to match the value of the function at 0, or the third derivative of the actual e to the x function at 0. So we have, I'm going to write it as 6c2 is equal to the third derivative of the f of x, the e to the x function at 0, which is 1, all right? So c2 is equal to 1/6. All right. So now we have our coefficients. We have all of the coefficients we need. Oops, that should be C3, right? C3. All right, so we have all the coefficients we need, so we can write our third order polynomial. P3 of x is equal to 1 plus x plus 1/2 x squared plus 1/6 x cubed. All right, there's our third order Taylor polynomial. How well does it match? Well, we can just compare, right? We can just put in a value near 0 and see how well it matches. So again, we'll put in 1/10. And so if I put that into my calculator, if I put 1/10 into the polynomial and calculate it on my calculator, I get 1.105167. And the value, of e to the x, if I put that into my calculator, is approximately equal to 1.105171. That's the same thing we got before. So that's a pretty small error, okay? If I take the difference between those two, P3 at 0.1, I get how many zeros? 0.00000. I think there's 5 zeros there. 4. All right, which is a tiny error, so less than 0.0004% error. All right, so that's pretty darn good. At least near x equals 0. You know, there's a lot of questions we might ask ourselves. How good is it? If you go, how far can you go out from 0 and have it, you know, how good is good enough? You know, depends on how you want to use it. But so there you go. There's a third order polynomial. And I'll meet you in the next video to talk about the general solution. And this is the solution that you're going to use when you're doing your homework. Okay, so we're going to come up with a general formula for a Taylor polynomial.